A great orbiting telescope floats serenely in the black, collecting light from the heavens above. It adjusts its field of view slightly, turning away from the nearby stars, and peers deeper into the darker reaches of the night sky. Beneath it, the planet turns, its white clouds swirling serenely in the faint stellar glow. And positioned as it is above the turbulent atmosphere, this telescope has an unrivaled view of the cosmos. Closest, just a few light years away, are individual stars, unique suns just like the one now hiding out of sight behind the planet. They cluster thickest in a wide, bright band that cuts the blackness in two. This is the galactic plane. Looking along it is to look to the center of the galaxy, some 100,000 light-years away. And the galaxy is an immense, flattened spiral, home to 400 billion suns. But the little telescope turns its gaze away from this blinding light. Looking up, above the galactic plane, the stars are more sparsely scattered, but the sky is lit instead by dim, multicolored smears. Each is a galaxy in its own right, containing billions of stars that burn just as brightly as those nearby, but whose intensity is masked by sheer distance. Mapping the positions of these diverse galaxies, the orbiting telescope sees a few dozen cluster loosely together in a local group. Deeper into the blackness, even dimmer smudges hint at more distant galactic clusters. With enough time, the telescope can map these too, finding that they cling together in even vaster superclusters, several 100 million light-years across, and bordered by gaping black voids, where no galaxies are to be found at all. And at the very edge of its magnified sight, the instrument glimpses the very edge of the observable universe, 45 billion light-years away. Thus, the structure of the universe is revealed in the simple curved mirror of an orbiting telescope. But this instrument does not orbit the Earth. It is a machine of another world, orbiting an alien planet that itself orbits an alien sun. The bright streak of the galactic plane is not that of the Milky Way, and the nearby galaxies are also foreign and unfamiliar. Our home planet is somewhere else in that extraterrestrial instrument's sights, although it would be almost impossible to pinpoint. There are no landmarks in the large-scale structure of the cosmos, no major differences from place to place that help us find our way. The universe looks surprisingly similar, wherever you happen to be looking from. It has broadly the same temperature and the same lumpy structure of dense, superclustered galaxies and hollow voids. Looked at from an omnipotent external point of view, where entire galactic clusters are reduced to mere points of light, the cosmos is remarkably uniform. But how did this come to be? How could such distant parts of the universe, separated by tens of billions of light-years, be so similar? Places so distant that they could never, ever have had any contact. It is a mystery that has plagued our accepted cosmological histories since they were written, a gaping hole in our understanding. Is our story of the origin of the universe incomplete? Or is this evidence of uniformity merely a freak occurrence, a bizarre coincidence localized to our view of the infinite cosmos? To truly investigate this mystery, cosmological detectives must take an explosive journey right back to the very beginning. We must probe improbable connections between the minuscule quantum world and the gigantic realm of superclusters, and open our minds to the even wider, even weirder possibility of a nested multiverse hiding within our very own cosmos. We must ask, what put the bang into the Big Bang? Or if the bang should even be there at all. About 13.8 billion years ago, the universe began. We don't know for sure how it happened, what it looked like, or how it behaved during its very first moments, but all of the evidence we have suggests that, at the beginning, it was very, very small, and very, very hot. Calculations by the physicist and priest Georges Lemaitre in the 1920s revealed that we live in an expanding universe, which, logically, must have begun much smaller than it is today. Subsequent observations have bolstered his mathematical viewpoint. The light from distant galaxies appears more red than it should do, as if the wavelengths themselves have been stretched. The further those galaxies are, the more red they appear, so the faster they are receding. Such a pattern could only arise if the entire cosmos were expanding, and had been since the beginning of time. Thanks to the finite speed of light, those distant, far reaches of the observable universe are also gaping windows into the distant past, and they too bear the marks of a smaller, hotter beginning. Based on this startling agreement of mathematical theory and highly precise observations, the so-called Big Bang has become the most widely accepted theory for the origin of our universe. But there is a problem. There are many features of our modern universe that don't fit with a simplistic, expanding Big Bang origin story. Not least, an infinitely small, infinitely dense, and infinitely hot beginning violating all known laws of physics. But there is more. There are features of the cosmos today that are very hard to explain if the universe had simply been expanding at a steady rate all this time. Thorns in the side of the Big Bang theory that threaten to bring it all crashing back down. The first is known as the horizon problem. An alien observer looking at the universe from tens of billions of light years away would see a cosmos almost indistinguishable from our own. In particular, the background radiation, which raises the average temperature of space to a few degrees above absolute zero wherever in the observable universe one happens to observe it. The chances of this being the case under a simplistic Big Bang regime are vanishingly small. The only way that the temperature of the cosmos can be so homogenized is if all parts of that cosmos were in contact long enough for them to reach equilibrium. A cold room with a single heat source in one corner will eventually reach an equilibrium temperature as the thermal energy is distributed evenly throughout the space. But expanding space-time does not allow for homogenization on such large scales. Energy can only be exchanged at the speed of light, and there has not been enough time since the beginning of the universe for equilibrium to be reached. There is no way that opposite sides of the universe can trade energy, because they are beyond one another's visible horizon. They are not, as scientists say, in causal contact. Running the cosmological expansion backwards, we find that parts of the night sky just 1 degree apart would have been beyond each other's reach at the time the background radiation was baked into the universe. How, then, did the universe get to be so homogeneous? Such an observation seems to require that the cosmological beginnings were finely tuned, with remarkable homogeneity from the very start. Yet the laws of physics and of statistics suggest that such fine-tuning is vanishingly unlikely. A second puzzling phenomenon seems to require this unlikely fine-tuning too. Known as the flatness problem, it is concerned with the intangible curvature of space-time. The fabric of space, as Einstein defined it in his theories of general relativity, is distorted by massive objects. But if concentrations of mass are responsible for curving space-time, then all of the mass in the universe must curve space-time as well. Depending on the density of the universe as a whole, the shape of that curvature and the long-term evolution of the cosmos varies considerably. If it is high, then the cosmological mass creates a spherical space-time, and the gravitational attraction between all the matter in the universe will eventually slow down expansion and reverse it. If the density of the universe is low, space will have an open, hyperbolic shape, and the gravity between matter will not be enough to stop it expanding forever. And between these two alternatives, there is a third possibility: a flat space-time, with just the right density for expansion to slow to a stop only after infinite time. This flat universe is a precarious balance between a cosmos that is too dense and one that is not dense enough, both of which are much more likely outcomes than the knife-edge intermediate. And yet, when astronomers measure the density of the observable universe, they find out that this most unlikely of outcomes is in fact our reality. To remarkably high precision, our modern universe appears to be utterly, invariably flat. There is no reason why it should be so. Any toss of the cosmos-creating coin is almost infinitely more likely to produce one of the other alternatives, but in ours, the coin appears to have landed on its edge. Was there something special about the universe's origins that set the stage for such precise balance? Or are our origin stories fundamentally incorrect? And one further conundrum needles the Big Bang theory of universal expansion. Despite extensive searches on a variety of scales, there appear to be no monopoles at all in the observable cosmos. A monopole is hypothesized to be just half of a traditional magnet, an isolated origin or ending of magnetic field lines without a corresponding partner elsewhere in space. We are well accustomed to dipole magnets with north and south poles and a magnetic field that flows between them. They are most simply represented by schoolroom bar magnets. Wherever we look, there is never just a north or a south sitting alone. This is a problem because there is no fundamental reason why there shouldn't be any monopoles. Not only that, but our current understanding of the universe's earliest moments suggests that the cosmos should be in fact flooded by them. But in reality, we find none at all. Together, the horizon problem, the flatness problem, and the lack of monopoles in the modern universe combine to call the entire Big Bang theory into question. How did the universe end up so homogeneous when it was too large for temperatures to equilibrate? How did the density of matter come to be resting on the near-impossible knife edge that renders space-time flat? And finally, what happened to all the monopoles? These are damning testaments in the case against the Big Bang, and ever since the evidence was discovered, cosmologists have scrambled to find an alibi, some explanation that could yet save the Big Bang history from its demise. In a small, low house in West Menlo Park, at the south of San Francisco Bay, Alan Guth worked late into the night. The Californian breeze stirred the pages on Guth's desk, uncovering sheet after sheet filled with fine, spidery writing of equations overwritten with annotations and overwritten again with wild thoughts and speculation. Guth was a smart man, but, he reflected, he was born at the wrong time. Part of the baby boomer generation, he found himself among fierce competition for academic work at every turn. In any other time, his dedication and insight into particle physics would have almost automatically earned him tenure at his pick of Ivy League institutions. And yet here he was, in yet another temporary post, working late in an increasingly desperate effort to get ahead. This time, Guth's work had brought him to the Stanford Linear Accelerator for a year to investigate the hypothesized grand unification of forces at the beginning of the universe and the mystery of the missing monopoles. His calculations were nonsensical to all but the most involved particle physicist, but that night he found himself in a flow that seemed to lay out the mysteries of the universe for him to understand in an entirely new way. As the breeze curled the corners of his workings, he was struck with a spectacular realization. A solution that seemed to demolish all objections to the Big Bang itself. The missing monopoles, the horizon problem, the flatness problem, all solved. If he was right, then this was an elegant cosmological thesis to rival that of Lemaitre, and Guth would never have to worry about finding work again. But Guth's late-night revelation was far from the first attempt to smooth the rough edges of the Big Bang theory. Back in the early 1930s, father of the theory Georges Lemaitre had put forward a suggestion himself, By now known as the famous Belgian scientist and a leader in cosmological physics, his remarkable observations on the beginning of the universe had made him a scientific celebrity. But Lemaitre did not rest on his laurels. Despite being praised by the Catholic Church for his apparent demonstration of a beginning, Lemaitre himself did not see it as such. The universe was like a phoenix, born, living, growing old and diminishing in flames, only to birth a brand new entity from the ashes. Lemaitre's Phoenix universe and its various incarnations as a cyclic cosmology, a big bounce, would help to resolve some of the inconsistencies in the Big Bang story. By repeatedly living and dying, cycling between expansion, contraction and expansion again, there is ample opportunity for the universe to reach thermal equilibrium, so that today, after how many rebirths, space itself appears utterly homogeneous. The horizon problem? Solved. Only this theory raises even more questions. Had our universe really lived and died countless times before the beginning of time, then there would be a record of it in time itself. The arrow of time is driven forward by the inevitable increase in entropy, in increasing statistical disorder from one moment to the next. So, if our current universe was just the latest in a long line of Phoenix universes, then entropy would have kept on increasing over all of those hidden lifetimes. The disorder of the current universe, therefore, would be so high that no structure could possibly assemble and persist. The Phoenix would live on, but each time it would be born older and older, until the life it leads is really no life at all. Other solutions have been proposed over the years to try and account for the various irregularities in Lemaitre's cosmological history. In 1969, a professor at the University of Maryland, Charles Misner, explored what he called the Mixmaster universe, so named after a popular brand of kitchen mixer. His idea was that the early universe went through a chaotic oscillation, and that this random and unpredictable motion, like that of dough in a mixer, would inevitably lead to a homogeneous, well-mixed cosmos. But the mathematics of such a universe are fiendishly and off-puttingly complex, and still, the issues of flatness and monopoles are hard to explain. So, it was a decade later that Alan Guth, in a moment of divine late-night inspiration, hit upon another, much simpler possibility. One that promised to solve the mystery of the missing monopoles, but also addressed the wider flatness and horizon problems in turn. What if, he supposed, in the earliest moments after the Big Bang, the universe had undergone a period of massive, accelerated, exponential expansion, before slowing down to its more moderate speed today? He saw that such an expansion could happen naturally at the end of the Grand Unification epoch, as a result of energy transformations as the individual fundamental forces split from the greater whole. So, when the universe was just a trillionth of a second old, space would have started to expand exponentially. Exponential increases start out modestly, but have the capacity to get very large, very quickly. One apocryphal tale tells of a ruler wishing to reward the Indian inventor of chess and asking him to name his price for such a wondrous new game. The inventor asked for wheat, 1 grain on the first chessboard square, 2 on the next, 4 on the next, then 8, 16 and so on, doubling the amount of wheat for each of the 64 squares on the chessboard. Scoffing at the apparently meagre payment for such a great invention, the ruler readily agreed, but his court treasurers soon realized the problem. By the time the board was filled, there would be nearly 18.5 quintillion wheat grains to pay, more than 2,000 times modern annual production. And so, the exponential expansion of space saw the cosmos get very large, very quickly. In around 100 billionth of a second, the universe doubled in size around 90 times. Such an increase would be equivalent to expanding a single red blood cell, 10 microns across, to a gigantic disk the size of our galaxy, more than 100,000 light-years in diameter. In reality, though, the early universe started out much smaller than any cell, or indeed any atom in our body. Various models disagree on the precise dimensions, but this massive expansion saw the cosmos stretch from a speck smaller than a proton to a respectable, roughly grapefruit-sized universe. This happened faster than the speed of light, a technicality that is possible in this case because relativistic constraints only apply to movements within the cosmos, not to the expansion of the cosmos as a whole. Alan Guth described this explosive period, the first real change in the appearance of the universe, as inflation. And suddenly, with this new inflationary defendant on the stand, things finally started to fall into place for the early universe. For one, inflation seemed to solve the problem of the missing monopoles. The physics of the grand unification of forces at the beginning of the universe required that monopoles be created in their droves when the strong force became distinct. This happened in a tiny early universe a mere fraction of a second old and little more than a Planck length across. Enter inflation and the near instantaneous expansion of the cosmos, including the mysterious monopoles, sees them suddenly and violently separated from one another, like chocolate chips embedded in an expanding loaf of bread. Today, after billions of years of expansion following that initial burst, space has become so large and the monopoles so far separated that we don't see them, simply because there are none within our observational reach. In a similar way, this spectacularly rapid inflation helps to address the horizon problem and the flatness problem. In all likelihood, there were massive differences in temperature of the post-Big Bang universe. But just as inflation distributed the chocolate chip monopoles of the universe, so it expanded all other elements within it too. The temperature differences of that early nanocosmos were near instantaneously flung apart. But we don't see these stranded variations. Our observable slice of the cosmos is only part of the greater, more inhomogeneous whole. The limits of the speed of light permit us only to see one small patch of the pre-inflationary universe that was in thermal equilibrium with itself. How similar or different it is to the rest, beyond our horizon, we cannot tell. Indeed, one study in 2011 calculated the true size of the universe as being 250 times the size of our observable section. That is 7 trillion light-years across. And this limited view of the vast cosmos also offers the solution to the flatness problem. It is vanishingly unlikely that our cosmos has the precise critical density of matter within it to render spacetime flat. But, with inflation in the mix, it does not need to. The universe is flat as far as we can see. But we are only seeing a small, inflated section of the greater whole. Thanks to inflation, our local area was made so big, so quickly, that all we see is flat plains, as far as the light speed horizon. Take a ball and scale it up to the size of the Earth, and even though you know the overall structure is curved, your view from the surface will always be flat. So, with a stroke, the introduction of inflation into the earliest moments of the cosmos seems to destroy any case against the Big Bang. From a single vantage point, much of the structure of the minute early universe is simply stretched out of existence. All temperature variations, exotic particles, and the very geometry of space itself disappear. And when inflation is finally exhausted, a decillionth of a second later, a disembodied observer would be left stranded in a cold, empty space that had seemed so full mere moments before. Just a few meters away from the South Pole, the stilted Scott Amundsen Station is illuminated by starlight alone. Just a few weeks into the 6-month-long Antarctic night, the temperature has already dropped to less than -50 degrees Celsius, and the wind howls around the curved building. From outside, the station looks abandoned, but a faint mechanical whir from the gigantic telescope dish gives away just the smallest sign of life. And inside the heavily insulated control room, only warm compared to the frigid night outside, a small team of scientists huddle in coats. They are among just a few dozen who have elected to stay through the months of this endlessly dark polar winter. Antarctic summers see the South Pole home to more than 200, but few would choose to brave the icy, dark isolation of this eternal night. But at nearly 3,000 meters above sea level, cold and dry air above the high Antarctic plateau allows the microwave telescope they control to scan the deepest reaches of the cosmos with unrivaled precision. Precise enough, they hope, to find an imprint of inflation itself embedded in the radiation that permeates all of space. As they pull their coats tighter about them, looking ahead to 5 more months of this darkness, they wonder what they will find. Because inflation, for all its problem-solving power, is still yet to be proven unequivocally. It has enjoyed widespread press and acceptance by the scientific community, being heralded as the first moment that truly unites the small and large scales of particle physics and cosmology. But it does more than that. It helps to explain how the very large-scale structures of the universe came about in the first place, from the smallest possible seeds. All of the stuff we see out there in space ultimately results from an imbalance of matter versus antimatter, mass versus vacuum, positive versus negative energy. While the large-scale temperature of the cosmos may be homogeneous, the distribution of stuff within it certainly is not. Huge galactic superclusters are bordered by yawning voids containing nothing at all. On the scale we experience it, our universe is one of contrast. But the origin of that contrast is not clear. How did all this variety spontaneously arise from practically nothing at all? Surprisingly, it is in the tiny world of quantum mechanics that a potential solution can be found. On the smallest possible scales, quantum particles behave in strange and inexplicable ways. One of these curious behaviors is described by Heisenberg's uncertainty principle, in which quantum fluctuations spontaneously create and annihilate virtual particle pairs, with no recourse to cause and effect. The pre-inflationary universe was small enough for such quantum effects to play a major role for the first minuscule fraction of a second. And when inflation began, the space containing those quantum fluctuations suddenly ballooned, rendering them vast beyond imagining, and sowing the seeds for the large-scale contrast we see today. From nothing at all, structure was created. Alan Guth himself described it as the ultimate free lunch. Indeed, 7 years before Guth's spectacular realization, the physicist Edward Tryon had proposed the idea that the entire universe could be created by one of these quantum fluctuations in a vacuum, truly born out of nothing. In answer to the question of why it happened, I offer the modest proposal that our universe is simply one of those things which happen from time to time. But constructing more theories that fit inflation is no true proof that the original theory is correct. What is needed is unequivocal observational evidence that this explosive expansion really did occur. And that is what the Antarctic astronomers were searching for in 2013. With the BICEP 2 telescope pointing deep into the South Polar sky, they were probing the fine-scale nature of the cosmic microwave background for remnants of that ancient time, known as B-mode polarization, which they believed could only have been created by universe-wrenching forces of inflation. And in March that year, they finally had their result. With great excitement, scientists from Harvard, Stanford, Caltech, and the University of Minnesota announced to the press that they had found their hallowed B-modes, created by gravitational waves that rippled out like shockwaves from the blast of cosmological inflation. It was a discovery worthy of a Nobel Prize, the culmination of 35 years of theory, prediction, and experimentation. But their joy was short-lived. As the months drew on, the scientists' confidence in their discovery waned. It appeared that inflation-induced ripples in space-time were not the only thing that could create B-mode polarization. Cosmic dust permeating the view of the South Polar sky had, it seemed, a major and unavoidable effect on the radiation they measured. So now, they push up their sleeves and prepare to try again. Other predictions for remnants left over from cosmic inflation have also failed to yield any tangible results. In the early 1970s, Stephen Hawking investigated the possibility of so-called primordial black holes, arising from gravitational anomalies in the very early universe, less than a second after the Big Bang. Once inflation took its place on the Big Bang stage, it was found that cosmological inflation could be an ideal mechanism for generating such primordial black holes. Not only that, but what could appear today to us as an ancient black hole could in fact contain entire baby universes, born of differing rates of inflation and isolated from our own cosmos by the limits of their observable universe. To the inhabitants of these baby universes, all would appear normal from within. They would exist within an expanding cosmos much like our own and believe that that was all there was. But to us, as omnipresent external observers, we are as gods, beyond the plane of their existence, able to see their bubble universe in its entirety. Yet the same light horizon that prevents those inside from seeing out also blocks our view through the looking glass. We cannot know whether these featureless black holes contain a hypercompressed singular mass or an entire living universe trapped just out of reach. It is another mind-bending prospect, that of a nested multiverse lurking right beneath our noses. But despite astronomers' best efforts peering into the blackness, the search, so far, goes unrewarded. We have not found any primordial black holes or baby universes. Inflation is on rocky ground when it comes to its mechanism too. Although Alan Guth's theoretical model suggested how inflation started, attempts to characterize its cause within the framework of particle physics have thus far failed. So the inflation field is thought to be communicated by a virtual particle, called the inflaton. But so far, no inflation field and no inflaton has been discovered. But the science is still young. The Higgs boson was only discovered in 2012, nearly 50 years after it was first proposed. Perhaps an inflaton discovery sits just over the horizon. Or perhaps not. American physicist Paul Steinhardt raised a glass to the assembled revelers in the bar. For a moment all faces turned towards him, and the cheer filled the room. But as his colleagues returned to their passionate conversations, the music swelled, and Steinhardt was left alone with his thoughts in the crowded bar. Today, Steinhardt's latest paper had just been accepted for publication, and as was tradition at the University of Pennsylvania, that meant the first round of beers was on him. His latest paper was a great boon to the university, to cosmology, and to the exciting new theory of inflation. He didn't know it at the time, but he would become one of the important pioneers, responsible in part for the great early success of inflation theory. And yet, even then, Steinhardt's mind was troubled. Everything he and his co-author had written in the paper was true, and rigorous peer review had probed his models thoroughly, but the implications of his work were disturbing. To make inflation work, they had to choose their parameters very, very carefully. If they didn't, their model cosmos created twisted multiverses time and time again. A seed of doubt took hold in his mind and began to grow. Today, Steinhardt has had a radical change of heart and is not shy about destroying that which he helped build. Inflation theory, he says, has introduced more problems than it was originally intended to solve. Worse, scientists are turning a blind eye to the theory's failings, and are themselves failing to properly scrutinize the concept, preferring instead to see it as an incomprehensible magic bullet. Inflation has been elevated to an almost religious status, a faith that gives cosmologists a comfortable peace of mind against the unanswerable mysteries of the universe, and has given rise to any number of misinterpretations and potential manifestations. And so, the situation must be serious for one of the theory's main proponents to become its most vocal opponent. And Steinhardt is not the only inflation apostate. They claim that there are now so many different models of how inflation could work and so many variables that can be endlessly tweaked that a true, testable inflation theory does not exist. Like the pseudo-scientific assertions of a creator, inflation has become undisprovable. Steinhardt reiterates that inflation was invoked as a way of avoiding having to fine-tune the early conditions of the universe. With inflation, the earliest Big Bang cosmos didn't have to be completely flat geometry, and didn't need to be completely homogeneous. But the physics of inflation now seem to require that same fine-tuning in order to produce the universe we see today. Analysing the fine-scale observations of the cosmic background radiation in 2013, Steinhardt and his colleagues calculated that there was less than 1 in a Googleplex charts of inflation producing the precise pattern imprinted in the universe. Inflation was supposed to give us a smooth, homogeneous cosmos, but in all but the most choice of models, it produces a terrifying multiverse of twisted, knotted, and enfolded space-time. Inflation is in trouble, but there is nothing quite ready to take its place. Alternative histories have been suggested, including a return to Lemaitre's Phoenix universe, if the entropy problem can be resolved. Steinhardt himself is a proponent of a return to this big bounce, cyclical concept. Perhaps the currently constant speed of light is blinkering us to the possibility that it could have behaved differently, under bizarre Big Bang regimes. Perhaps the birth of our universe is merely a ripple in a higher dimensional bulk of hyperspace. All of these alternatives have potential, but are rooted in physics we are not able to understand right now. Perhaps we never will. And perhaps that is why so many scientists still cling to inflation, despite its flaws. At least it can be described within the realms of a cosmos we can comprehend. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave a comment to tell us what you think. I will see you next time.